Alright, this is crazy because I included it in an Anki card, but alright, this is a quick tutorial on how to draw and understand the leads. I'm putting it here to kind of just remind myself of this concept. Alright, so remember the EKG has 12 leads in different places, but for now let's just consider lead 2. And remember, so you have the Eindhoven triangle or whatever, and this is going to be your right, it's going to be your left, and that's going to be your foot. And right here, you can have one from right to left, so positive, negative. You're going to have one from left to foot, so it's going to be negative, positive. And you're going to have one from right to foot, so that's going to be negative, positive. This one right here, going to be lead 2. This is going to be the main lead they use for EKGs and the one we're going to review here. This one right here is going to be lead 1, kind of a horizontal view, and this one right here is going to be lead 3. Right, and if you remember on the body we also had a VL, we had a VR, and we had a VF, and these leads were the unipolar, while these leads are the bipolar, and these leads together make the hexaxial system. Right, this makes the hexaxial system. And remember, the hexaxial system doesn't include the precordial leads, which are also very important, and they're in different areas across your chest precordial region. So if we remember here, there's one lead right here, which is going to be your, that's going to be lead 1 at 0 degrees. Right, you're going to have another lead actually at 90 degrees, but the main trick you use here is every 60 degrees. So every 60 degrees, it separates a bipolar lead. So at 60, you're going to have lead 2, and at 120, you're going to have lead 3. And I drew these angles horrible, but it's kind of like it should look better. At 90, you can have AVF, and these are 120 degrees apart. So 120 degrees apart, 120 degrees apart, that's minus 30, that's minus 120, and that's going to be your AVR, or yeah, AVL, and that's going to be AVR. So that right there is your hexaxial system. I didn't draw it well. But if I bring like a better drawing, you see it right here. You see it right here. All right, so that's basics. Now what we're gonna do is actually I gotta explain the basics of the leads and the vector. So remember, your vector is going from negative to positive. And basically we have a voltmeter here, which is your EKG measuring each vector. For bipolars, you have a probe here and a probe here. You actually have 2 physical probes. For unipolars, you just have one probe on the actual body, and then you have another probe that's set at 0. So it's not actually on the body, right? And now you have your voltmeter here. And so what happens is your voltmeter does, so the negative is your reference, and the positive is your measuring. And what the voltmeter does, it does positive minus the negative. So let's say this one is plus 90 and this one is 20. Your difference would be 70, right? So now when we're coming into understanding the action potentials, when we want to understand what the action potential does, when the action potential goes, so inside the cell, let's say this is a big cell, you have, it's typically negative, right? Around negative 90 for these heart cells. But remember, this is measuring the extracellular concentration because it can't actually go inside the cells. And so outside the cells, it's going to be positive. So regularly, your cells are going to be positive. So what happens here is that when you have an action potential, so let's say this is your measure, this is your reference, so this is your negative end, and this is your positive. this is your measuring, and that's the voltmeter. So what happens is, let's say we have an action potential, right, and it's starting here. So what happens is the inside becomes positive, but the outside now starts to become negative. And the action potential travels. So at the start of your action potential, it's going to be negative at your reference, and it's going to be positive at your measuring. So what happens is, when you do positive minus negative, it's actually going to be a greater difference, right? At this point, the voltage is 0. We can all agree the difference is 0. It's both positive. But at this point, this is negative, this is positive. You do positive minus negative, you get positive. So on your EKG, it's going to start to look positive. And then eventually, the action potential will fully spread, and it will go back down to 0 when it's completely depolarized. That's kind of like your P wave, but this applies to every concept. And now, when it repolarizes in a normal cell, so let's say we have all negative, what happens is, typically in normal cells, it's going to repolarize here. So it's going to start positive, and this part's going to still be negative. And now you're going to do negative minus positive. That's going to be a negative number. So it's going to start to go down, and then eventually everything is going to become positive, and it's going to go back down to 0. Now, a key concept, you need to understand that in the ventricles only, the repolarization starts in the more distal cells, the cells that were depolarized last, right? Because the Purkinje fibers, when the Purkinje fibers are firing, what happens is you want all the ventricles to contract at the same time, but it has to go through the whole ventricles. It has to go through the whole ventricles, right? And so you don't want them to, have the same conduction speed, and then suddenly this one will fire and then it'll relax while these ones are still contracted. That would mess up the blood flow. So if you want them to all relax at the same time, these ones, the more distal cells, they got the stimulus later than everyone else, right? They got the stimulus later. So you're gonna have them have less of a refractory period or whatever, and you're gonna have them depolarize quicker. And so they are going to depolarize quicker to make everything kind of happen more at the same time. So I hope that explains why that happens. Now let's go over like the electrical process. So let's say you have, again, the negative and the positive ends, and you have the cell. And now this is a completely depolarized cell, so that the outside is going to be negative. Now let's say this positive end is measuring the distal part of your ventricles. What's going to happen is you can have repolarization here first, while these are going to still be depolarized, right? So what happens is you do positive minus negative. Instead of a downward curve, it's going to be an upward curve. And then again, the same concept applies, where they end up becoming repolarized again, and it's going to be normal. So this is going to explain everything when we get to the actual leads. So this was all actually covered in lecture. I understood most of this in lecture, not really, but I'm trying to help you all out and help myself out. So now we're going to get to the real stuff, right? So we're just going to do this with one lead, and there's a Ninja Learn video where I pretty much learned off all of this from, but I'm trying to apply it to lecture. So what you have is this lead, right? So let's draw the heart. So I'm going to draw like a really bad heart, but let's say this is your heart, right? And then you have like your atria on top. But the main point is, this is the apex, so this is going to be left side of the heart, this is going to be the right side of the heart, this is left ventricle, right ventricle, septum, and then right here I'm going to draw your SA node. So what happens here is, let's draw lead 2. So remember, if this is the right arm, lead 2 has its negative end on the right arm, and the foot, which is going to be down here, as is positive, or it's measuring right here. So its vector is kind of going to be going this way. And then you remember, like, lead 1 would be going more right to left this way, and then left to down would be lead 3. But let's go over lead 2 because that's the most commonly measured one. So what happens here is we're going to have the initial SA node pacemaker, 75 per minute, whatever, it's going to be firing. And when it fires, it's going to mostly go to the left because it's already on the right. So the vector on the right side isn't going to be as bad. So you're going to have like a net kind of vector that's kind of going like this way, pretty similar to your initial what you're measuring. So the vector, remember we said if the vector is going in the same direction for depolarization, if the vector is in the same direction, it's going to be a positive thing. So that's going to be your P wave right there. Right, and the P wave is your atrial depolarization. And that's because at this point, you're going to have cells turning negative first, while here it's going to be still positive. And so it's going to do positive minus negative, it's going to go up, and then eventually all the extracellular portion is going to be negative, and it's going to be the same. So you can apply that concept to everything. Now the next thing is you're going to, you have your depolarization, and this will repolarize. But the thing is, the second this repolarizes, it's going to be during your ventricular contraction, so it won't be measured. So now you have, it goes down right here, interventricular septum, right? When it's going down your septum, it depolarizes the left side first, and then it goes left to right, left to right. So you're going to have like small vectors going this way. And that's because, I actually forgot the reason, but it just wants to do the left side quicker, I guess, because it has more to get to on the left side. So your overall vector for this portion is going to be more this way, right? It's basically going to be opposite, right? So you make that, and it's going to be opposite, right? It's pretty much going to be opposite. And so remember, when we have an opposite vector, these parts are going to turn negative first, the outside, and this part is going to turn positive. And when this turns negative, positive, you're measuring more this side first, so you're going to have to do negative minus positive, you're going to get negative. And then eventually they're all going to become negative, but what happens is you're going to get that little drop. Right there, that's your Q wave. So now it's spread down, and this would be your more bundle of His area. Now it's spread down, and you want to kind of get your ventricles, right? So what happens is you can get more of a vector towards this way, right? Because most of your left ventricle is much bigger than your right. So you're going to get some vectors this way, but it's basically going to be an overall net vector in the exact direction that you're measuring, because it's trying to get to the base of the ventricle. This is a big base. And remember, when it's going in the same direction, this part is going to become negative first before this part. So you're going to get a nice big R wave, right? It's going to spread to the whole thing. So that's going to be your R wave. Now you have the kind of superior portion of your ventricles that hasn't been filled up yet. So you still get some spreading to this area. Not as significant, but what happens is it pretty much makes an opposite net vector, right? So this part is going to get depolarized first, so it's going to be negative. This part's going to be negative, while this part's positive. You're measuring at the positive end, so you're going to do negative minus positive. That's going to be negative. So it's going to go down. Again, it's going to be your S wave. Right, so S wave. This whole QRS complex, that's going to be ventricular depolarization. P is going to be atrial depolarization. Boom. You've done that. Now, once you've done that, what happens is you're going to move on. So you're going to move on to, and so this portion, you're going to have some time where the ventricles are basically just contracted. And remember, we have that isovolumetric contraction, and then after that, I'll actually explain that later. But basically, you're going to have some resting period, and then you're going to have to repolarize. So the interesting thing is, I already mentioned, the more distal parts repolarize first, right? So the repolarization, instead of going this way, it's going to be going this way. And repolarization, so you can have these positive ones, they're going to turn negative, while your initial cells are going to be positive. They're going to be, right? So, I'm sorry. So right here, it's going to repolarize this way. And so what happens is you're gonna have, it's gonna turn from negative to positive while these cells are still positive. Hold up, I'm tweaking. My bad. So forget what I just said. So basically, we don't really factor in the more superior patient portions. So you're gonna have repolarization, and it's gonna be more in the opposite direction, mainly like this direction, right? Because it's gonna be more from your base to your septum. This is gonna actually kind of be going this way, but because it's so little compared to your base, which is where most of your repolarization is occurring, the net vector is gonna be going up. This is gonna be going opposite from here. And so what happens is the cardiomyocytes at the base are going to repolarize first. So they were already negative, right? Because they were depolarized. But now they're going to become positive, right? Because cell membrane returns back down to negative 90, and so the outside becomes positive. While these are still going to be depolarized, so the outside is still going to be negative. So this was your negative end, this was your positive end. You're going to do positive minus negative, and you're going to see, oh, look, it's going to actually be going up. And then eventually they're all going to become positive again. And that's going to be your T wave representing ventricular depolarization. So that was kind of explaining the whole vectors in the EKG. And so remember, you can use the same logic, right? The arrows are going to be the same direction every cardiac cycle. But if we moved the positive and the negative here, like in lead 3, it would change a little bit of the waves. Now the thing is, actually lead 1 and 2 and 3 pretty much have the same thing. But when you look at like the precordial leads, if I change the direction 180 degrees, right, it would show the exact opposite, right? It would show something, it would show something different. So you can use this exercise and use other videos, but this was kind of to explain what we needed to know